Welcome to Study Loop.
This is the answer to Chapter 14, problem number 19 from the Smith Organic Chemistry textbook. And in this problem, we are asked to determine the structure of two molecules. So we're asked to identify A and B, which we're told are isomers of molecular formula C3H4Cl2. And we're given NMR data for each of these molecules. And so the first thing to do in a case like this, where we're given a formula and asked to come up with structures, I always like to start by calculating the hydrogen deficiency index. So that's going to look like this. So HDI equals 2 times the number of carbons plus 2. Minus the number of hydrogens, and then in this case as well, so we need to minus the number of halogens, so two chlorines, and then all of this is over 2, and so 6 plus 2 is 8, minus 6 is 2, 2 over 2 is 1, and so we have one ring or one double bond in these molecules, and I'm going to go ahead and say that it's probably a double bond. It could be a 3-membered ring, a cyclopropane, but it seems unlikely. So I'm going to proceed under the assumption that we have a double bond in each of these molecules. So then looking at A, we have 2 signals. I've ignored the coupling constant here because it doesn't really tell us much. So the coupling constants are the same, which tells us that these 2 signals are splitting each other, which is kind of a given in a molecule this small. Okay, and so as I said, we can assume that there's going to be a double bond. So I'm going to go ahead and draw a carbon-carbon double bond. So we have one more carbon to account for. We have to place these 4 hydrogens, and we have 2 chlorines to account for. So looking at our signals, our first signal for A has a chemical shift of 1.75, is split into a doublet, and accounts for 3 protons. And so the easiest way to account for 3 protons is going to be a methyl group. So I'm going to go ahead and put a methyl group here. So CH3. And then our other signal is shifted pretty far downfield, 5.89. It also accounts for only 1 proton. And so I'm going to say that that's a proton on a carbon that's participating in this double bond. And because it's splitting this methyl group, it is going to have to be in pretty close proximity. So I'm gonna put this on the same carbon here. Okay, and so having done that, all that's left is to put our 2 chlorines here and here. And so that's the structure for A. Okay, so then moving on to B. Again, just like in A, I'm going to proceed under the assumption that we have our double bond here. So this time we have 3 signals. And so the first one accounts for 2 protons. The second 2 account for 1 proton each. And so the second 2 signals are pretty far downfield again, 5.42 and 5.59. And once again, I omitted the coupling constants here, but it's 1.9 for each of those 2 signals. So once again, they're splitting each other, and each of these signals is a doublet. So I'm going to go ahead and say that these are 2 protons on one of these carbons in the double bond here. So I'm going to say H and H. And that's our signals 2 and 3 right there. Okay, and so we have 2 more protons to account for. They're accounted for by a single signal. Also fairly far downfield at 4.16. So I'm going to go ahead and say that we have a CH2 right here. And then we'll put one of the 2 chlorines there and the other chlorine here. Okay, and so this is a good structure for B. It accounts for all of these signals. All of the shifts and the splitting makes sense. And so, yeah, that is, in fact, the correct answer for B. Okay, and so that's the way to approach this problem. Again, I think whenever you're given a formula and asked to draw a structure, that you can't go wrong starting with an HDI. And then we just need to consider each of the pieces of spectral information that we're given. And that's the answer to chapter 14, problem number 19.